Welcome everyone. Lecture number 2, Combinatorics of posets. Today the main theme is dimension and planarity. So in general there is like a belief, hope, wish, project that posets that look nice should have small dimension. Yeah, what does it mean nice? Maybe you can draw them in a nice way. Maybe they have some structure. Given that, our measure of complexity should behave well. And what does it mean that it behaves well? Is it bounded absolutely or bounded in some parameters? We'll touch this topic today. But instead of doing like a survey and going over the landscape of results, I elect to just show you 3 or 4 proofs, yeah, of some cornerstones of this topic. And when we are done with that, most likely within the next lecture, we will do a nice slow overview over the topic, and you'll see where are the challenges and what would we still like to understand better. Given that, we need to understand a little bit better how to bound the dimension from above. We spent some time last lecture bounding the dimension from below. In general, this is a very tricky business, and not much more in terms of techniques is known than the things I have shown you. But from above is obviously a different story. And the first tool that we use almost always when we do it is we discuss alternating cycles. So what are they and why are they useful? So when we look at the dimension problem, it's about constructing a realizer. What does realizer do? It reverses incomparable pairs. Every incomparable pair should be reversed by one of the linear order in the realizer. Yeah. When you look at this subset I of incomparable pairs of our given poset, we say that it's reversible if there is a linear extension that reverses all of them. Yeah. So there is something that respects the poset and yet kills all the relations that you are looking at in I. Yeah. And then you can rephrase dimension to be the minimum integer d such that the set of all incomparable pairs of the poset can be partitioned or covered. Actually, this is what we used to do by d reversible sets. Yeah.
And here the pairs are ordered.
Yes. The pairs they are ordered, and yes, xy as well as yx as soon as they are incomparable, both pairs are in the set. Yes, good point. And that's the same, but slightly another angle on dimension. Maybe note that this works if the set of incomparable pairs is non-empty. If it's empty, this is the same as to say that a poset is a chain, dimension is 1, and life is beautiful. Yes. So it becomes interesting if we kind of understand what does it mean that the given set, a subset of incomparable pairs, is reversible. And we do have a very good understanding of that. And that's where alternating cycles come into the play. So an alternating cycle is a sequence of incomparable pairs of our poset. So xi, yi, say we look at the sequence of length k, such that xi is less or equal yi plus 1 in the poset. Yes, so okay. So and this should hold cyclically. So here you look at the healthy alternating cycle of size 4 incomparable pairs. Yeah. And you see what relations are required for this to be. The vertical elements aligned vertically are incomparable pairs. Yes, the 4 incomparable pairs. So now I'm not claiming that there are no other relations in the poset. They could be within an alternating cycle, but often we find useful to discuss strict alternating cycles, and there we require that there is absolutely no other relation. Yeah, which boils down to the thing that xi is less or equal yj if and only if j is what you expect, so it's I plus 1. And this again holds cyclically, yes, if I didn't stress it, so the last x4 in this figure is below y1, yes? Yes. So now, what's the connection? A set is reversible of incomparable pairs if and only if it does not contain an alternating cycle. And since it's quite easy to see that given an alternating cycle, you can find there a strict alternating cycle, perhaps shorter, the 3 items are equivalent. And since this is a really a thing we use all the time by default with you know, on the fly, let's see the argument. So 2 directions. First, we start with a set which is presumably reversible, and we want to argue that it does not contain an alternating cycle. So suppose the opposite, suppose it does. Yeah? And since the set is reversible, there is a witness for that. So there is a linear extension of the poset, respects the poset and flips all the incomparable pairs in I. And there should be a problem immediately. So the problem is that when you look at the so this linear extension should reverse our pairs from the alternating cycle. So yi should be below xi in the linear extension. Yes, but linear extension also should respect the poset, and xi is below yi plus 1 in the poset. So we have a strict inequality yi less than yi plus 1, and this holds cyclically for all I in k. That cannot be. Yes, so if a set is reversible, it does not contain an alternating cycle. And now suppose that now we want to prove the other implication, yes? So in order to do that, consider our poset relation P, and take our pairs I, and so here by ID I mean the dual of I, yeah? So if xy is in I, then yx is in yd, ID. And the claim is that if we take the poset relation and take a union with ID, then this is acyclic. Assuming that I does not have an alternating cycle. Okay? So we need to prove that, right? So so this will be proof of claim. And what do we do here? So suppose the opposite, yes? We claim that some relation P union ID is acyclic, yeah? So supposing the opposite, we should find a cycle, yeah? We should consider a cycle. So here is a cycle. How does a cycle look like? So, so there are, so say this is red, okay? So there are edges coming from P, say they are white, and there are edges coming from ID, say they are red, okay? Do I have a better chalk? Not really. Yes, so P and ID. So it looks perhaps like this. Yeah. Now, what do I? That's just an illustration. What I claim that whatever cycle I take, I need at least. I need at least one red edge, because P is a poset relation. There are no cycles over there. What I want to say is that there are at least two red edges. So edges coming from ID. Why is it so? If there would be just one, what does it mean? This is from ID, so this is an incomparable pair in the poset. But yet all over the cycle you have P, which witnesses that this element is below this element. That cannot be. So if there is a cycle, there must be at least two red edges, okay? So let's look at this cycle, and let's pretend that we know what we are doing. So say this element is x1, and this element will be y2. x1 is below y2. This will be x2. This will be y3. This is going to be x4, which, yes, that's okay. This is going to be, no, I missed some index. x1, y2, x2, y3. This should be x3, which coincides with y4. This should be x4, y5, x5, y6,
y1.
Thank you, Michał. Yeah. What do you think about this? I say it's an alternating cycle. Yeah. Xi is below yi plus 1. Yeah. And look at the pairs xi, yi. Aren't they on the red edges? Yeah. Always from y to x. Red edges are in ID. This means that xi, yi is in I. Yeah, that's an alternating cycle with all pairs in the poset with all pairs in I. But this was our assumption that there is no alternating cycle like that. So if there is no alternating cycle, this thing is acyclic. That completes the proof of the claim, and that pretty much completes the proof of the implication, because if this is acyclic, well, you can take a transitive closure and then you can take a linear extension of it. That's our L. And then what can you say about L? One, L is a linear extension of the initial poset, because it respects even more, not only the poset but also something else. And two, L reverses all pairs in I, because it respects ID. So that completes the proof of this proposition, which says that which exactly describes what are the subsets of incomparable pairs that are reversible. So we have a pretty good understanding what can we kill in one go. Yes. So on the again at the dimension problem, you can take this angle that you want to cover the set of incomparable pairs with these kind of reversible sets. So sets of subsets of incomparable pairs that do not contain an alternating cycle. Yes. So now we are jumping into the business. So we and we already right at the first slide we get a cooler. Yeah, because the claim is that nice looking posets should have small dimension. Yeah, planar graphs have chromatic number at most 4, and that's not the case. Yeah, there are planar posets of arbitrarily large dimension, and let's just look at it immediately to adjust to this situation. So this is the best known construction, I think, by Kelly from 1981. And well, you see that the diagram is planar. I hope you kind of see what is the definition of this family here, how to expand it, to have it larger. Now, what we should convince ourselves about is that dimension of it is large, and this will come simply from at first mind-blowing fact that we have a standard example here as a subposet. So standard example, something like a complete bipartite graph almost, embedded in the plane. Yeah, but in this poset fashion, yes. So using transitivity, it becomes possible. So what we should note here is that these red elements at the bottom, the A's, and at the top, the B's, they induce a standard example. Here we have a standard example of size 5, and since dimension is monotone, this Kelly example has dimension at least 5, and general dimension will be unbounded. So observe this element A3. Look at its comparabilities. Yeah, you can go to the left and collect some B's of indices lower than 3, and you can go to the right and collect B's with indices larger than 3. So A3 is below all the B's except B3, and this is the case for all the A's. So we really have a standard example here. Another thing that I'd like to note at this point here is that it's not only the planarity, it's also the tree width here is very small, even the path width. Yeah, and I'm not going to argue or draw with you a path decomposition because it will kill some time. It is really elementary. The intuition that I have in mind that convinces some of us is that you can peel this graph like an onion. Yeah. So yes, that's Kelly example. So on one hand, you might say, okay, it's something negative, yeah. But the truth is that, especially nowadays, it makes this stuff. There are so many open questions because of that, yeah. And the conjectures and the problems they get because of the fact that this is simply unbounded, yeah, and to kind of understand what drives this dimension here in the regime with planarity is an exciting topic. So yes, but still we can prove something if we are given a nice poset. And the first thing I would like to start with you is a result that if you have a planar diagram, so like Kelly, but you have a zero, you have a single minimal element, an element that is below everything, then suddenly dimension becomes bounded. So the first sanity check is, wait a minute, maybe we can plug a zero to this poset. You could, but then it's not planar anymore, right? So if you have a planar diagram and you have a zero, dimension is bounded. And the proof is very instructive, we do it now. So, first of all, given this poset fix a planar diagram, yeah, let's talk about one concrete drawing. And now, within this setup, when you have an element, so this unique minimal element, let's call it x naught, okay? And now, given any other element z, yeah, z is above x naught, yeah, and in the planar regime, yeah, when you have an element, perhaps it sends some edges upwards, yeah. In the planar diagram, these edges must go vertically monotone upwards, yeah. And perhaps, well, and for sure, if z is not the zero, it some edges are arriving here from below, yes. And now, given this element z, I would like to describe you the region of z, which I hope is very intuitive thing. Yeah. So you first you take the left chain of z. So starting from z, you go to 0, but you kind of stick to the left as much as you can. Yeah. So always taking the leftmost edge in the diagram down, and eventually you get to 0. Yeah. And the same you do from the right side, and you have right chain of z. And then this region here, I like to call it region of z. Please note that we might have some degeneracies, you know, the left chain and the right chain can meet. Yeah, they can even go together at some point. Yeah, so things like this that are possible. This still I would call a region of z. Okay. Yes.
What if z only has like one chain downward?
Then this region is like you know, it consists only of this boundary, and then the interior is empty. Yes.
The chains belong to the region.
Yes, yes. It's they are the boundaries of that region. So now you know what is this business about? I mean, we have incomparable pairs, and all we're going to do is we're going to partition them or cover them with reversible sets. So we need ideas how to split the set of incomparable pairs. So in other words, we need some properties of incomparable pairs, yeah? So these are left and these are, you know, green, yes, and yes. So and then this comes pretty natural in this setup. So think about an incomparable pair xy. Yeah, I would say that xy is a left pair if I see one of the setups above. What do I see here exactly? So given two elements x and y, I don't know what are their vertical coordinates. Yeah, so I have two cases. Yeah, here on the left side I have x, which is drawn above y. Yeah, and on the other case it's y that is drawn above x. So if x is higher in the diagram, I remind you they are incomparable in the poset. Yeah, but still x, the vertical coordinate of x is larger. Then xy is a left pair. When I draw this region of x, I hit the horizontal y line left of y. X is left of y. Doesn't it look like it? Yeah. And then, but then if y is the one which is drawn above, I would say that x is left of y because x is left of the region of y on the x line. Yeah, that's a definition. And also, I would like to say that a pair is right if everything is right, and you should note that you know, if xy is left and yx is right. Yeah, this should be fairly clear. But these are not the. I mean, given an incomparable pair, it doesn't have to be left or right. Yeah. Did I? Yes, I did. I didn't mention you. I mean, this is like an illustration of a poset that we want to show that dimension is most free. Yeah. You can see here like an element here which is incomparable with this element here. Yeah. And you see that this is not left, not right. Yeah. It's under or above, yes? So an element, a pair is under, an incomparable pair is under, yes? If the region of the second coordinate of y contains the region of x. So yeah, there are some things to say here, right? Well, I could define it that the region of y like hits the x line on both sides of x, yes? But I mentioned, I wrote here actually containment, and this is true, because the reason why it's true, I mean, in theory, it could be that this region of x goes out, yes? I didn't argue that, but it doesn't, right? It does. Why it doesn't? Because if you look at the left chains, you see a forest. Well, a tree, sorry, because everything goes to x naught, yeah? If you look at the right chain, you see a tree again. Yeah, it is very easy to argue. But once two left chains meet, they never split, because there is always one leftmost direction to go. Okay, yeah. So indeed, this is about containment of the regions here. Yeah, and the dual of an underpair is an overpair. Now we have all the possible cases, which should be again pretty clear, and that's how I would like to split the set of all incomparable pairs into 4. Yes, dimension at most 3. That will do it, but let's simplify our life. Yeah. Let's split them into 4. So which one are the easiest? What's your intuition? Which one should be the easiest to reverse?
Under.
Under is the easiest to reverse. Given that you have x and y, what is more natural in a linear extension? That first you see x or first you see y? I would say x, yeah?
Yeah.
Okay, so it means that it's easier to reverse over on our intuitive level. Yes? Because somewhat it's very inviting to put y before x, because it is, yeah? And yes, so I over is reversible. And there is actually a strikingly simple argument, yeah? Just when you have your planar diagram, read the elements vertically from below to above. Read the y coordinates, yeah? First thing to argue, it's a linear extension. Yes. Second thing to argue, all over pairs are reversed. Yeah? Easy. Okay, let's do something a little bit more substantial. Let's show that all the left pairs are reversible. The set of all left pairs is reversible. So here we need a little argument. Let's do that. So claim I left is reversible. Proof. Oh, let me clean the other board. How do we prove it? Suppose the opposite. So it's not reversible. If it's not reversible, there is an alternating cycle. So consider an alternating cycle, x1, y1. If I remember well, it will be handy to take actually a strict one. A strict alternating cycle with all pairs from I left. And we should get somehow a contradiction. So how does the alternating cycle look like? So you have a pair xi, yi, and xi is below yi plus 1, yes? How do we see it in the poset? Well, xi, yi is a left pair. So this is one of the possible two drawings that we had in the definition. Here. It's a left pair. So let's draw one of the drawings. So we have xi, we have the yi line, yeah, and we have a region of xi going to 0. Now, let's take I plus 1. xi plus 1, yi plus 1, yes? No. Yeah, why not? Now consider where is in this picture, where is xi in this picture? Xi in the poset is below yi plus 1. Yeah? Well, okay, so the relation goes downwards. Yeah? Possibly xi you see here. Could you cross the region? Could you be somewhere here, for example? Would it generate some problem? Yes. Then xi would be below xi plus 1, which is not the case in a strict alternating cycle. So indeed, xi is somewhere here on the plane. And now look at the left chains. That's the left chain of xi plus 1. How does the left chain of xi look like? Well, we don't really know, but the thing we want to argue is in this tree of left chains, the chain to xi branches right. We should look at the other case. So where is xi? Well, here we have the whole region of yi plus 1, xi is below, so xi must be in the region. I don't care if it's above this line or below this line, irrelevant. It's somewhere. But definitely in the region, because it's below y plus 1. And then again, just note that whatever is this left chain, it actually doesn't leave the region, because this is some left chain and left chains form a tree. Yeah? So whatever you see here, it looks like this. Again, in the left tree, in the red tree that I'm drawing here, yeah, the branch of xi is right of the branch of xi plus 1. And this holds for all I. That cannot be. If you have some question, don't hesitate. So, okay. So that was to argue that I left is reversible. Now, okay. Let's do it properly. Let's argue that I left and union I over is reversible. Yeah. I mean, this I over was silly anyway. Yeah. So let's put them here. So the argument will be pretty much the same. Yeah. I left union I over is reversible. So I just now I should take a strict alternating cycle in the union. So my pairs here could be left or over. Yeah. And I'm going to argue the same thing, that the branch of xi is moving right in the left tree. So if I have a left pair, yeah, if xi yi plus 1 is a left pair, I have it. So I should have a look at the case when xi plus 1 and yi plus 1 is an overpair. So xi plus 1 is above, and yi plus 1 is here, right? So where is this is an overpair. So where is xi in this picture? Well, xi is below yi plus 1 in the poset, yeah? So it is attached somewhere here. Can it leave the region? No, because then you make xi comparable with xi plus 1, which is not the case in the strict alternating cycle. So xi really lives here. And then when you consider its left chain, yeah, maybe it does some crazy stuff, but if it hits the left chain here, it agrees with it because left chains form a tree. Yeah. So again, you have this picture, and you have a contradiction in a more general sense. Okay. So I left is reversible. I right is reversible. I over is reversed anyway. I under is something that we didn't discuss yet. Right? I under is reversible. So the proof is the same, the setup is the same. Proof, suppose the opposite, consider an alternating cycle with all pairs in I under. All pairs in I under. Yeah. So let's take one of the, so alternating cycle xi, yi. Let me draw it in the plane. So it's an under pair. So xi is here and yi is somewhere above, right? And the picture looks like this, yes? Yes. So I think I want to go to yi plus 1. Yeah, so this is x naught. My question is, where is yi plus 1? It is above xi in the poset. So we go. Yeah, we go. Can we get through here and go over there? That looks like a big problem. xi is incomparable with yi. You cannot do that. Well, so this means that yi plus 1 sits here. Yeah? So now I please note that the vertical coordinate of yi plus 1 is less than the vertical coordinate of yi. And this holds for all I cyclically. So I under is reversible. Very good. So this put together should give us the proposition theorem. Yeah. After all, we covered all incomparable pairs by 3 reversible sets. Yes. Dimension is the most free. So the 0 gives you some forces, some topology to happen, and then it kills the complexity. Yeah.
Can you
Yes.
you state it by like ordering these regions according to some, for instance, the rightmost point or something like this?
Yeah, it is always a challenge to phrase these arguments in a way that they are formal and readable or understandable. I kind of felt I did it like formalizing the region with its left boundary, because I was looking at the left boundary, yeah, and I found that this thing increases in the monotone fashion, and so could you even reduce it to a single element? I don't know. I kind of don't see it. Yeah. If you have something in mind, we can discuss it. Yeah. But that's the easiest I can do this argument. Yes. So we proved this one, and we have a nice corollary now, because yes, Samuel.
If you have 2 relevant elements, is the different theorem positive? Okay, then the dimension arbitrary.
Tom, would you like to answer? But in general, dimension in a planar diagram, dimension is bounded by a function of the number of minimal elements.
2 times it minus 1.
And this is some research from 2018, pre-COVID.
So 2 times and minus 1 is uncomfortable.
Yes.
Yes.
Type for T was 1, 2. That's the effect. But proof for 2 is hard. And after that, T plus 3.
Yes, good question. Good question. As I told you, I elected to show you some arguments here. Yeah, there are some statements, but it's more about these arguments at the moment. But if you look from the angle of the posets and the simplest posets you can think of, and is the dimension large or not? I mean, those that the cover graph is a tree or a forest come to mind, right? And dimension over there is bounded, and this is actually a corollary of the thing we just proved. Yeah. So think about a poset that has that the cover graph is a forest. Yes. Well, how does it look like? Is the first question. Well, I'm drawing it already like a diagram. Yeah, something like this. Yeah. Okay. That's the object. Dimension at most 3. Why? Well, take your favorite element, yeah, and root the tree. We do it component by component. Root the tree in this element, yes. And now I want to redraw it in a way that I can see it. So now there are some elements perhaps that are lower. That have a cover edge to y, and they are lower than y. And there are some elements perhaps that are larger than y and send the cover edge over there. Yes? So what I would like to do is, one by one, for all elements that send edge downwards, draw this edge and draw a little box inside here. Yeah? Completely private. Yeah, where I'm going to draw, the next element, and I'm going to recursively draw the rest here of this tree. Yeah, here, 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 and then I elect to do those that are larger than y. And the invariant I keep that whenever I have an element, the vertical ray down is uninterrupted. Okay? So I keep it here, and by induction I have it all here, for all elements here. Okay? So that's my poset. And now I plug a 0. Yes? Dimension at most 3. If your cover graph is a forest. Inside, because I don't know, spider exists, and if you, instead of drinking beers, you actually did something yesterday, you proved that dimension of this is exactly 3. Well, the exercise was that it's more than 2. But given what we know now, we can stop there. Okay. Altiplanar cover graph. When I have less time, not like this week, I sometimes just do this proof. It came later, but somehow given, and it's a a broader class of posets. But the bound is 4, and somewhat the argument is very like visible, and one can fast forward it and still give some intuitions. So yes, let's do this one. Well, okay, maybe a little pause. Autoplanar cover graph. This is a really good moment to stop and tell you that this is also about this poset. It doesn't look autoplanar at all, right? But remember, cover graph. Yeah, I drew you a poset, a diagram of a poset here. Yes, and there is no way to draw this diagram in an autoplanar fashion. But the cover graph itself is autoplanar. Clearly, you can put out these diamonds and put them around the vertex. Yes. So that's one reason I drew this poset. The second reason is that it actually witnesses, if the number of diamonds is large enough, 20 something, right? Then it witnesses that it is tight. And this is a fun exercise to do. See you in the afternoon, right? Yes. So that's dimension 4 in the autoplanar case. Let's look at the argument. So what do? We take this cover graph G of our poset. It is autoplanar. So now I want to draw it, and I want to draw it really not respecting the poset. I want to use the autoplanarity, so I want to put all the vertices on a single line in such a way that all the edges are drawn in one of the half planes, say the upper one. Okay? And now when I have, remember, I want to cover a set of incomparable pairs with reversible sets. When I have an incomparable pair xy, this is pretty clear what I mean that x is left of y, right? Or x is right of y. Yes? Okay, so we split incomparable pairs into 2, yes? Two subsets, yeah? Let's take those that are left, yeah? So here we have an incomparable pair, x left of y. This is yet not reversible. We need to specialize. So look at such an incomparable pair, and we will say that it's active. If something like this happens, if there exists z in the poset, such that z is below y in the poset, and z is left of x on this line. So that's the reason I have this path here, because if z is less than y in the poset, there is a covering chain starting from z and marching towards y. Yes? And this, if I step by step I use only cover relations, then I see this as a path in the cover graph. So I'm claiming here that there exists a path from y that reaches left of x. Then I say that this pair is active. And if I don't see anything like that, I see this pair is not active. Okay?
So here it shouldn't cross the edges, I think.
Okay. I went a little bit too far here. Very good point. Yes, it's an autoplanar drawing. Apologies. Yeah, the edges shouldn't cross, and this will be important in a moment. Thanks. Thank you. Yes. So we split left pairs into active and non-active, and we claim that both sets are reversible. Yes, they are. Claim I left active is reversible. So suppose not. If it's not reversible, then it contains an alternating cycle. Take an alternating cycle with all pairs in I left active. Alternating cycle all pairs in I left active. Okay. So let's draw this. So xi is left of yi, but the pair is active. Let's fix this witnessing thing, and now let's try to not do anything silly. Or maybe, because this will be a little bit simpler, let's do this. Okay. Yes, so I see that I want to look at yi plus 1 here. So in the poset, yeah, this is an alternating cycle, so xi is below yi plus 1. Where is yi plus 1? Where is it? Yeah, let's walk on the path in the cover graph from xi to yi plus 1. Yeah, we can wiggle around, no problem. Can we kind of leave this bounding area? Well, we cannot cross edges, yes, that we already established, but there is an option that we could leave through the exit points, like here, or maybe we can touch this one or this one, yes? Can we? We are walking upwards from xi, and whenever we hit any element here, we can enter the path that still goes upwards to yi. xi is not less than yi. We cannot do that. So we eventually stop somewhere. And what can we say? Where is yi plus 1? yi plus 1 is left of yi. And this holds cyclically for all I and k. Contradiction. So, yes?
Is that argument depends on the particular representation of the graph, because that's how you are doing
Yes.
finding it.
Yes, it does. It does.
So,
The first thing you do is you fix this. Well, we're working with a poset with an autoplanar cover graph, and the first thing you do is you fix this embedding of G on this line. You fix it. You take a particular one, and the whole argument is working on that thing. Yes, yes. But whatever you fix, I can deliver here. Yes. Okay. So this set is reversible. Let's take the other set, because there is no symmetry here. Yeah, I cannot say. I will tell you that it's symmetric for the right ones in a moment, but in the case of non-active left ones, we still have no idea what to do. Claim I left non-active is reversible. Okay, so how we prove that a set is reversible? Suppose the opposite. Consider an alternating cycle with all the pairs in the set. x1, y1, xk, yk, alternating cycle with all pairs in I left non-active. Okay, let's draw this. So we have a line. We have xi, which is left of yi. What do we want to do? Xi minus 1, right? Because xi, yi, I need to go from... Yes. So, my question is, where is xi minus 1? Where is xi minus 1? Well, xi minus 1 is below yi in the poset. If you elect to go in a path with a path in the cover graph, you start and good luck. You go, yeah? Can you go here? No. Okay. So xi minus 1 is right of xi. And this holds cyclically for all the I in K, which cannot be. So the set is reversible, and we partitioned all the incomparable pairs into 4 reversible sets, so dimension is at most 4 in this case. Okay. I think I will enter here a longer argument, which is supposed to be the last one in this section. Perhaps I will not close it here, but I don't think it will be a dramatic problem. So let me.
Excuse me. Is there
Yes?
a tight example of this?
Is there what?
Tight example.
That's the
Ah,
example.
okay.
This one. We'll do it in the exercise session. Ramsey theory is your friend. Okay. So this particular result was kind of inspiring in the sense that from there we took it and we understood that this is not only about planarity, not only about height, many directions. But what is the result itself? So you see large dimensional posets are white, as Dilworth said, but not necessarily tall. There are planar posets with arbitrarily large dimension, but the thing is that they have to be tall. And this is stated here, because there is a function such that for every h, which is your target height, and every planar poset, or poset with a planar Koppe graph, we'll get to this distinction with, let's not talk about it at all. We have that the dimension is bounded by a function of height. And so I'm not going to show you the argument from the original argument. I would like to show you something which you could see is a kind of generalization of these ideas on the orderings. Yeah, we had the autoplanar graph situation.
The second orange word was meant to be tall.
Yes, yes, of course. Yes, tall. But they are also white. Yeah. Couldn't resist. Yes, so here you have a statement which also bounds the dimension by a function of height in a planar setup. Yes. No. Not in the planar setup. Not at all. All we want to know is that the specific parameter, parameterized by h, so the height, is bounded. And taking that, we'll get the bound on dimension itself. So this parameter is something that some of you know pretty well. Let's quickly go over this. Yes, it's about weak coloring numbers. So hey, we have a graph. We have a linear order of vertices on the graph. We have fixed a natural number r. Now we can say that one vertex is reaching the other vertex if something specific happens. Yeah, so u is r weakly reachable from v. If starting from v, you can go along a path in the graph. Yeah, so that there is this linear order which I depict on the axis. Yeah, there is v, there is a path. I hope. Yeah, and then eventually I reach u. When do I really do it in the fashion that is acceptable by our weakly reachable regime? Well, first of all, the path is not too long, at most are edges. Second, U is the leftmost on all the path with respect to sigma. Then the set of all vertices that you can R weakly reach from a fixed vertex is this set W reach R parameterized by G, the graph, sigma, linear order. It pretty much depends how you order. So this is fixed. And the vertex V itself. This is all the U that you can reach in this way. V belongs there as well, because there is a trivial path that satisfies this. And then the R weak coloring number is the best you can do. So the quality of a linear order is measured by the worst vertex, and vertex is bad if it can reach a lot. We would kind of try to bound it, yeah, that there are not too many things left on the left, yeah. So the quality of a fixed ordering is the vertex is the size of the largest weakly reachable set, yeah. And then you take a minimum over all linear orderings of their quality. Okay, if you see this concept for the first time, this is a little bit that's something to digest, yes. What can I say in like 30 seconds? Well, I can tell you that this is a family of parameters that is obviously monotone. So W equals 0, W equals 1, yeah, and so on. I can tell you that this is trivial, this is always 1. I can tell you that W equals 1, it actually coincides with something that you should hear about. It's a degeneracy. It's a coloring number, so degeneracy plus 1. Yeah. Coloring number of a graph is you take a linear order and you look at each vertex, how many neighbors he sees to the left, plus 1, and then you take the best ordering with respect to that. Yeah. So this it's pretty clear that it should coincide with the thing here when R is equal 1, and it does. And then these parameters grow. This family of parameters actually captures something which is heavily studied over last decade. Maybe we get into that in the survey part of this course, like tomorrow or something. I can tell you also, if you give up the R and you put infinity there, so you don't put any restrictions on the size of the path, this also coincides with something that we know, which is the larger 3-dep, which is 3-dep, yes? Yes, so yeah, that's it. From our perspective, the only thing we really have to know at the moment is that that this family, well, it was introduced almost 20 years ago by Hal Kiersted and Dachin Yang, and this is bounded for planar graphs. Yeah. So we do know that the degeneracy of planar graphs is at most 5 or 6. Forgive me, this plus 1. Yes. But whenever so for R equals 1, this is bounded by a constant. But then for any given R, you can bound it. Whatever is the planar graph, you can bound it by a function of R. And this function is actually something we can consume. It's a polynomial. Yeah. The gap is small, but still very annoying. And I would love to see it close one day. Anyway, because of the upper bound here, this bound is meaningful for us in the planar cover graph setting. Because here in the assumptions we have that weak coloring number, the 3H weak coloring number is bounded. Yeah? And then instead of that, if someone gives me that I have a planar cover graph, then I know that the free h recurring number is bounded by a cubic function of h. So this cubic function of h jumps here, and I have a single exponential upper bound on the dimension in the planar case, in terms of the height. Okay, 1 minute break. Okay, so what are we doing here? We have a poset P, height h, and we know that. So we have its cover graph G, cover graph of P, and we assume that we know what is the weak coloring number of 3h minus 3 of G, and say that it's most C. Then we want to argue that the dimension of P is at most 4 to the C. Okay? Let's try to proceed with this setup. So yeah, let's fix that this is exactly the thing. Do not get confused. Now weak coloring number is small, so we need to work with that. So let's take the witness, which is the linear order that witnesses that the weak coloring number is small. Yeah, let's call it pi. Pi is a linear order on VG, witnessing this. Okay. Now. So what does it mean that it witnesses this? That this means that for every V in VG, we have that the W reach of 3h minus 3 G pi V, the size of it is bounded by C. Yes, that's what it means. Now it is pretty often that when we are working with that, we are considering a greedy coloring of vertices along this linear ordering. So this is what we want to do here. So let phi be a coloring of the vertices of G, so of elements of P as well. A greedy coloring of VG, such that it goes along pi. And what it does is, when this goes along pi, when this is already colored, and you look at the vertex V, what you want to do is you want to color this vertex with a color that you don't see in its W reach 3h minus 1, 3. Yeah? And since you know that its W reach is of size at most C, and this is including V itself, then you have at most C minus 1 colors blocked, so you can do it with C colors. Yeah? In such a way. And so you kind of avoid, when you want to color V, avoid colors from W reach G pi V 3h minus 3. Yeah, because all of them are colored except V. And okay, so we use at most C colors. Very well. Now, observation. when you have X an element of P, and you have two elements Y and Z that are in that can be reached from X, but in a short distance, not in free H, but in H distance. Yes, so from X, so G by X. Now I need these elements to be distinct. Then either Y is reachable from Z, or Z is reachable from Y. And therefore, the color of Y is distinct from the color of Z. And this is a pretty elementary statement whenever, if you ever did anything with recoloring numbers, you've seen such a statement. What do we do here? So we have the ordering pi, yeah. We have X sitting here, and there are two objects that we reach, Y and Z. We don't know the ordering. Say that Y is left of Z, yes, because that's how it is in the alphabet. And then you can reach it. So there is a path. There is an orange path that does something like this, and there is a purple path that I don't know, does something like this. Yeah. So the thing is that this alternative comes from the assumption which one is left of the other. Here in my picture, it will be Y that can be reached from Z, and you need double the distance because the witness is the union of two paths. Maybe it's shorter because maybe these paths intersect, but at most 2h minus 2 edges you use. And yes, and as such, since you are still in the 2h reachability stuff, and the greedy coloring was done in the 3h, this means that when we were coloring Z, we were avoiding the color of Y. This means that the colors must be distinct. Okay. Worked. Okay, let's move on. So this was all related in terms of a graph. We didn't look at the poset yet, and we need to kind of accommodate the thing that we have some relation that is in behind this graph, and put it together with this linear order of the abstract cover graph. And this is what I'm going to do here on this board. So I'm going to look at the upset of a vertex of an element X in my poset. Yeah, and I call it weak upset. And what do I mean by it? Well, I definitely want to have elements Y that are in the upset of X. I'm not sure if I ever use this notation, but U of X is the set of all elements above X in the poset. If I use these brackets, I mean that X is included, okay? So I really want elements to be really above. So this simply means that I want Y greater than X in the poset, yes? But not only that. What I want is that there is a witnessing chain, so let's call it a covering chain. There is a covering chain Q from X to Y. Yeah, since X is less than Y, there is a chain. Yeah, but a special one, such that the minimum on pi of q is y. Okay, so we have two angles. We can look at the poset, and here is x, and here is its upset, yeah? And some elements, perhaps, are in the weak upset. Yeah, maybe this one, this one, this one, yeah? When is it so? Well, you need to look at the pi then, yeah? And x is somewhere in the pi, and then this is in an upset. Maybe you have a chain here. And within this chain, if you go along this chain, say this chain is green, yeah, maybe you jump around, yeah? But eventually, when you hit y, you are leftmost. Okay? This means, in particular, that not necessarily all the elements on the way are in the weak upset. Yeah, because simply they could be right of x even, yes? Okay, so this is a weak upset, yes? And then I also have a weak downset, which is pretty much clear what I mean. It should be the set of all y's in the downset of x, such that, and then everything is the same, but a chain goes from, well, it's a chain down, yeah? So from x to y, downwards, and again I want to have that minimum pi q is y, yeah? So pretty much the same thing. Weak upset and weak downset. So please note one thing, that that these paths that are witnessing that something is in the say weak upset are chains in the poset, and as such they are of bounded length. They are, h is our setup. We are in the bounded height situation, so at most h minus 1 edges. Yes, that's simply because we are walking on a chain. Now, now what do I need to note before we do some real business? Well, I want to note that the weak downset of x, as well as the weak upset of x, is contained in the set that we can reach. Now, we need, as I said, we only need to take h minus 1 steps, and we are walking in g pi x. Is it clear? This containment. Is there any question here?
Yes, just I'm not sure about my intuition, but is it the case that the only difference here and there is that here edges are somehow oriented in the posets?
Here and
So you
there.
have to,
What does it
like-
mean here and there?
Okay, so weak reachability, we take edges in the cover graph, so we can take edges going up or edges going down, and on the
Yes,
left
yes,
we have
yes.
to always
Very
go
good.
up, right?
Yes, yes.
Yeah.
Yes, yes. Very good. I should phrase it this way. Very good. Yes. Okay, we got it. And then this containment is again clear, right? Now there is another thing I want to spot here. So say that you have element x in P, and consider some I that is a color of something that exists, say, in the weak upset of x. Yeah. So again, I have x, and now consider red. There is an element that is in the weak upset of x, and it's red in my coloring. Yeah. I is red. What do I want to tell you? I want to tell you that there is only one red thing in the weak upset, and this is my element. There are, yeah? If there is a red thing, there is only one. And this will be a consequence of this observation. Okay? So, there is a unique element in W, U, X of color I under V. Yes, there is one because I just took a color that is in the thing, so this is nothing deep. But the thing is that it's only this one, yeah. And this indeed comes because if there is another red guy, yes, like here, yeah, then you take this path and the union of these two paths connected at most 2h minus 2 edges. Well, that's the observation stated there. They have to be of different colors. Okay, so I would like to put in this setup. So if I have x and I have fixed I, then I can tell you that I have an element that I call. Let's change the colors. I call W U I of x. Yeah. So this is like an element witnessing the ith color in the weak upset of x. Yeah. And then I have the same I. If it exists, it's unique. So I put a name on it. Okay. And now we are ready to at least put the claims that we want. So, what are we doing here? We are bounding dimension. Yes, so we want to partition or cover the set of all incomparable pairs, yeah, into reversible sets. Yes, so we consider x, y, which is an incomparable pair in our poset. Yeah, basic step. And now I want to give a type on it, like a color. But since I have already a coloring, I will say that I put a signature. Okay, so define the signature of xy as ABC, a triple, where well, A is the set of colors that you see on the weak upset of x. B is the set of colors that you see on the weak upset of x and the weak downset of y. B is a subset of A. C is a subset of B. So these are these colors from B, such that when I look at this element of color I that is in the weak upset IX, and when I look at this element of color I that is in the weak downset of Y, I know how do they look like in pi. So say they look like this in pi. Okay, and then all we will do here is that all pairs for every ABC, all pairs of this signature, the set of all pairs, is reversible. Yeah, you fix ABC, you take all the pairs with this signature, it's reversible. This will be done deal. Why? Well, what remains counting, right? Okay. How A colors? How many colors? C. So this is our set of colors. Yeah, A is a subset of it, B is a subset of it, C is a subset of it. How many possible ABCs do we have? 4 to the C. That's why all we need is this claim. Every given set like that of a fixed pairs of a sixth signature are reversible. Yes?
Wasn't C supposed to be like W
we there is a chance that I put the wrong number on the board, but I believe that we started the proof. We say let's fix pi to be witnessing this weak coloring number, the your weak coloring number, so 3h, and then let's do the greedy coloring with respect to this size of reachability sets. So the coloring is done for 3h. Now the observations were done for 2h, h. This was happening later in the proof, but the pi itself and this greedy coloring is for the 3h. Yeah. So the number, so the c, this constant that appears in the statement is this weak coloring number that we talk about, the 3h minus 3,1.
And that we have 3h will be used now.
Yes. So it wasn't yet. I mean, the heart of the proof is coming still. Yes.
Yeah. The whole reasoning so far would work for 2h.
For 2h's. Yes. Indeed. Ay. Well, yeah, I mean, it's never a good moment to stop, right? But it's like one page of my notes, which should be within 10 minutes of a lecture, but I don't think it's a good style to go over time. Yes. So maybe with this statement, I will just do some closing remark. What should be the closing remark? So so my goal here was to, and still is, to show you some concrete arguments for concrete bounds. For a moment, these statements are a little bit scattered. Yeah, you see, this is bounded, something is unbounded. Yes, and I do it, and later on I will give you the full landscape that I know, or everything that I think is relevant that I know. And then I hope you can relate to some of these bounds that you've seen, what is working here, what is working there, and which directions are open and still interesting. Yes. So that's what's going to happen next time, and later we will see. Thank you.
I should remember it from your paper, but is this functional bound also true for lower dense posets, or like posets with lower dense homograph?
No, it's the dimension there is bounded by n to the epes. When epes, so the same was what you should expect, right? And then it takes a completely different argument because, as you know, when you put a bound in lower dense, it's not meaningful. Yeah. So it was a separate story.